Anyone? Give it a guess. Chewe. Okay, let's think about it. We can do some research. Do a mini research here. I think we looked at this anyway, but not in this context. Maybe you've just forgotten. We look at it in a different context. But you can just let's all research on this and have the answers by next. Okay, so we come to the production of pig iron. You have your blast furnace here, your iron ore. So you have your iron ore, that is, it's crushed, isn't it, into what are known as pellets, or through this process where you achieve sinter. And the limestone is also crushed here, okay? So you have the iron ore, the raw materials here in the production of pig iron is what, or just iron is iron ore. You have your iron, your rocks containing iron, which are known as the iron ore. Then you have your limestone, calcium carbonate, and you have coal. Okay, so you have calcium carbonate here, and then you have coal here, which the main composition of coal is what? Carbon. Okay, so you have iron here, and you have carbon here, and you have carbon here. So there's a sinter here down to your gas uptake. And then you have your core here. Also is the crushed. And then these three raw materials are entered into, or they are fed into the blast furnace. You have your exhaust gas here. So as the temperatures are rising, you have your gases there forming up, and they are through the exhaust and through a scrubber here to clean them up. And then there's a cooling mechanism that happens, and before they're released into the air. So this sinter is what we probably call today center. When people say, hey, you see center and whatnot in the air, and there's that intoxication of sulfur and what. This is the process that this is where the weight comes from. Not really center. Okay, so you have your furnace here, and you have your three raw materials there. And then what do you have at the end? So when your processes are happening at a certain temperature, we'll look at the temperature in detail later. So what happens at the bottom there? So you have your slag, which is a byproduct, which is at the bottom, isn't it? It's removed from the bottom there. And then somewhere in the middle there, you have what you're interested in, which is your molten iron. Here, molten iron is released into these structures, these modes. And then this raw iron, okay, straight from the furnace into these modes. This is what is known as pig iron because of these buckets. They're known as pigs, basically. So this is how you achieve that name of pig iron. So it's just raw molten iron when it's put into these, when it's put on these modes. That is what is known as the pig iron. So coming to temperatures, I think the next slide will have going down. I think we should have the temperatures exactly. Yeah, so the vertical shaft furnace is called a blast furnace. It's a vertical shaft furnace, as you saw in the diagram. So you have your iron ore, you have your coke, and limestone. They are charged. So coke coming from the core there, iron ore from your iron ore, and limestone also mixed as the third raw material. So you have your hot air for approximately 1,200 degrees Celsius is pumped into the bottom of the blast furnace. So you pump in hot air, and then the limestone attracts impurities, and the slag forms and floats on top of the molten iron. So those the slag is basically the impurities coming from the iron ore that form and they float on top of the molten iron. And this iron is drawn off or tapped and poured into modes known as pig iron. So that iron now, your molten iron, is what is tapped into these modes, which are known as pig iron. The common ions here that we have, that so the common ions, these are the name of the common ion, the names of the common ions, that's hematite, magnetite, limonite, and siderite. Those are the very varying compositions of iron in them. As you can see, the highest composition is hematite iron, which has a composition of 70% iron, which is a common iron ore. So the most common iron ore that we have in nature is hematite. Sorry, it's not even hematite, it's a magnetite that has the highest composition, but the most common is a hematite, while magnetite has the highest composition of iron, but not very varying, 72 and 70%, not very different. Okay, so this is how, these are the temperatures in the blast furnace. So as your hot air is pumped, your feed is from the top here and your exhaust gases out this way. So compressed air coming through and your molten iron is here being collected through this outlet. So whatever is coming here on top is slag. These are just impurities that are skimmed out on the left side. And then these are your temperatures. So the hottest place here is below, which is 1900, 13, 1850, and 500 here at the top. So these gases, before they're released into the air, into the atmosphere, they have to be cleaned first, they have to be treated, and then cooled off. And at 500 degrees Celsius, these are the processes that happen. So your iron ore there, plus carbon monoxide, forming up these compounds. And this compound plus carbon monoxide, you achieve your byproduct. Your main byproduct is carbon dioxide. At 850 degrees, you have an iron ore here. I mean, you have an iron compound here forming up, which is iron oxide, plus also the gas here that is produced is carbon dioxide. Same thing here. So from there, at 1000, what happens to this particular compound when it mixes with carbon monoxide? The oxygen molecule moves to the carbon monoxide, leaving a pure form of iron, okay? And then now you have two molecules of oxygen forming carbon dioxide on this end. So this is how you achieve your molten iron ore. And at 1300 degrees, what happens? Carbon dioxide plus carbon will give you two atoms of carbon monoxide. At 1900, you have carbon dioxide and carbon monoxide here, and a freed up atom of iron. So you have more molten iron achieved here at this process at 1900 as well as at 1000 degrees Celsius. So this is maybe another simpler way to look at it. So you have your coke, iron ore, and limestone being fed into the blast furnace into a refractory vessel, as it is known. Then you have your molten iron there being achieved, your slag, air coming through there, your hot air being fed into the system to heat it up. Then you have the layers of coke and iron ore forming. So heat generation, reduction of iron ore to a metal is happening here. Purification. Remember, you have limestone. This is calcium carbonate. This is limestone. This is the process. This is the slag. Calcium oxide here is basically what is slugging up here on top. Okay, as well as the aluminum oxide here also forming up with silicon dioxide, which is coming from an iron ore, and the calcium oxide, which is coming up from the breakdown of your limestone. So Coming to the production of steel now. Steel, in, like we discussed before, very essential to everyday life. Like we said before already, what is steel made out of? A various range of equipment and anything that you can name, from spoons to bridges to refrigerators, are made up of steel. So the raw materials there for steel production are what? Iron ore, coke. So this coke is made from specialist coking coals and small quantities of limestone. And then steel is produced by processing iron through the basic oxygen furnace, or the BOF as it is known, and the electric arc furnace, which is the EAF. So I remember what we said, steel is made up of. Steel is basically iron alloyed with carbon, a composition of carbon, not more than 7%. So this is how it's done. I know it's a bit difficult to understand here, but there's a video that I'm going to share with you on YouTube that goes process by process, to show you exactly how it happens in industry. And you have a much, much better overview. If you've not seen this already, you have a much better overview of how exactly this happens. So in the video, you're going to see the section mills, the plate mills, the hot strips. All this is going to make sense to you. I think if I describe it here, I'll have a tough time, but when you watch the video, you're going to see firsthand how this happens. And when you read alongside these notes, because I think you already, no, we don't have this. So when I send you this presentation, plus the video that you're going to watch, you're going to have a much, much better understanding of what is happening here. Otherwise, I'll struggle in vain trying to understand and help you imagine things. So this is steel production in the basic oxygen furnace, or in the BOF. So these are the charging raw materials, and this is the input. This is the blue side, the composition of the hot metal after pretreatment. You have the figures there, the mass percent. And then this is the output now, amount of gas collected, gas composition. This is just an idea, just to give you an idea of how this happens. Then this later on goes to secondary refining. So this is the charging scrap. All this you're going to see in the video. How the slag is scrapped off, just to try and achieve a better quality of steel there, and how it's put into these molds, tapping and slagging, sampling just to see whether you've achieved what you're looking for, desirable properties have been achieved with the steel. It's tapped here and taken to the lab. So now this is steel production in the electric arc furnace. So it basically looks like this. It's also a furnace, except it's electric. The other thing that makes it different is that it has this arc shape here at the bottom. Okay. So you also see how this works in the video. But these are just basically it has electrodes, the anode and the cathode. Also, they're aiding in producing a purer form of iron. So you have the charging scrap, you have the melting here, the additions here. So some additions are added there, as well as slugging is happening here, as well as tapping on the other end. So you see that also in detail. What else is worth noting here? So this is just basically describing the process and the reactions that take place during the solidification of an ingot, which is a solid form of the shaping of a molten steel into a solid form. So the solid form of steel is known as the ingot here. And then what happens to the rejected oxygen? So the gases, most gases are ejected during the solidification of the metal, because the solubility limit of the gases in the metal decreases sharply as its temperature decreases. So with decreasing temperature, if you remember the phase diagram there, it has the solubility lines there. So as you are reducing your temperature, you're crossing those lines, and then gases are being ejected from your stew. So the oxygen is one of the gases that is ejected. So this rejected oxygen combines with carbon to form carbon monoxide, which causes porosity in the solidified ignite. So it's ignite. Depending on the amount of gases evolved during solidification, 3 types of steel ignites can be produced. These are cured, semi-cured, and rimmed. So you have a better understanding of that, how that happens also. So you have the continuous casting process. You see this also. I think I wish I wish I sent you the video earlier, because I think it would have made this lecture easier, because you would have already had a picture of how this happens. Anyway, we have our types of steel here. I'm mostly interested in, and we have this, the phase diagram. Remember the iron carbide phase diagram. So this is what we looked at earlier, and we have found it here. So you have the cementite, austenite here, and the ferrite happening here, and the detective points, just like we looked at it earlier. Then we have this. This is more in detail, showing us the temperatures, and in more detail, the types of solids that are forming here. So you have cementite, perlite, and transformed ladebarites at the bottom. Then you have these ones here that are worth noting also. So you need to know what is forming where in the phase diagram. You need to know at which section what is formed, what type of steel is formed. So what I'm interested in you knowing is, this is also important, is the uses for steels. So as you can see, tensile strength, hardenability, additions. Okay, so for example, for medium carbon here, you have heat treatable flame, and then what's added? Chromium, nickel, and molybdenum. Okay, an example is this one here. And then hardenability, meaning it's hard, it's strong. And then ductility, no. And then with the uses there, you have pistons, so ductility is low, pistons, so uses gears, and wear applications. So basically, you need to know at least the uses, the applications of the different types of steel. So moving from here to there, you are increasing strength. So when you increase strength, you're increasing cost while decreasing ductility. So as you're moving from low carbon to high carbon, from low to high carbon, as you are increasing the carbon, what are you doing? You're also increasing the strength of the steel. It becomes more costly. However, ductility is decreasing. Remember what I said, when you cross from 7% carbon going further, you add carbon more than 7%, your steel becomes brittle, and you won't really have basically any use for it. That's why most steels are produced below, with the carbon content below 7%. So if you can just know the basic applications here of the different types of steel, that would be good. So this is just showing us the classification of carbon steel designation system. So these are the figures, the codes that you see on different types of steel. For example, a knife, you usually see these digits, these codes. I don't know if you've seen them before on different types of steel tools or equipment. So the last digits is signifying, the last 2 digits are signifying the carbon content. For example, it's 0.4%. Then the 0 is the modification in alloy. So it's plain carbon. So if 0 means the plain carbon. And then the 1 here means what? It indicates, 1 indicates carbon steel, 2 and above indicates alloy steel. Okay. So there are two classifications, the American Iron and Steel Institute, AISI, together with the Society of Automotive Engineers, SAE. They've established these 4-digit designation systems. So you have this system. Okay, so 0 plain carbon non-modified. 1 is resulfurized, so sulfur. 2 is resulfurized and rephosphorized. So phosphor and sulfur added. 5 is non-resulfurized. This is manganese content over 1%. Last 2 digits indicate carbon concentration is 0.01 degrees Celsius. I mean 0.01%. So an example is this one. Okay, so let's look at this one, for example. Quickly, shall we? Let's work together. Have you seen this example? SAE. Let's try and see what this one means. SAE 1030. SAE 1030. Let's try and figure out what it means. So the one, what does the one mean? Sure, are you there? Look at this example.
Yes, sir.
Yeah, so one, look at this example one. What does the one mean?
Indicates the alloy steel.
Carbon steel. 1 indicates carbon steel, while 2 and above indicates alloy steel. So if it's 1, it means it's what? Carbon steel, isn't it? So it's carbon steel.
Yes, yes.
Then 0.
Plain carbon.
Plain carbon.
Yes.
Okay, and then 3, 0. The last 2 digits.
Carbon content.
Of what percentage?
0.8%.
0.3. 0.30%. Okay. Let's try another one. Let's try another one. ASI B1020. Anyone to give it a try? Let me come back here. So meaning it's the American Iron and Steel Institute, okay? That's what it means. And then, who wants to give it a try? Eunice. Please give it a try. Please give this one a try.
Yes.
So let's start. B, what does B mean?
Carbon.
Okay. Then 1.
Is it steel?
Yes, carbon steel. So B means this one, carbon acid Bessemer, okay?
Yes.
So a letter prefix before the 4-digit number indicates the steel making technology. So A is alloy, basic open hearth. B is carbon acid Bessemer. C is carbon basic open hearth. D is carbon acid open hearth, and E is electric furnace. Okay. So making B here, we get it from here. So 1, what does the 1 mean?
One will get it from down.
Means carbon
Mm.
steel, isn't it? Yeah, you
Yeah,
mentioned
carbon
it earlier.
steel.
And 0. What does this 0 mean?
Modification.
Mm,
Plain
That's plain carbon.
plain carbon, isn't it? And then
Yes.
the 2 and the 0.
For the 2, someone to help me.
Carbon content.
So the last 2 digits here symbolize what they represent. They represent carbon content, okay?
Also,
So in our
20% of carbon content.
0.2. Remember what we said about
0.2.
carbon? It can't be more than 7%.
Okay.
So 0.2. So 40. For in our example, we had 40, meaning 0.40.
Okay.
So meaning for this one, it would be 0.20.
0.20.
20.
Is that helping her? Okay, 0.20. This one. So you can go through, look for any, usually knives. The Chinese like to put these codes. Just look for anything metallic, even in your kitchen. Try and read these symbols. Okay, try and I'll send you these notes so that you try and practice what these codes mean and what they represent.
Okay.
Yeah. Which reminds me of one thing. We need to cover one particular subtopic. I think under mechanical properties we do not do. That is important also. Well, we look at hardenability also, the HB. You need to be able to interpret the codes. I think we'll look at that when we meet in our physicals, or maybe online we'll try and cover that material under mechanical properties. Okay. So for this one, I know I cruised, but most of this is just material that is required by you to be able to just, to learn, okay? It's pretty straightforward. So I'll leave this with you. I'll send it through your class rep so that you go through the presentation, and I'll send you a link to the video so that you go through, you watch through the video and have a better understanding of this production. It's very interesting. And once you watch the video, and maybe even any other video that you can see online, it will give you a better understanding of how this happens. So metal, remember, when we look at ferrous and non-ferrous, we had a similar diagram. You have non-ferrous metals and you have the ferrous, steels, low carbon, medium carbon, high carbon. Then there's the low alloy and the high alloy. Okay. So high carbon here, plain and full stainless. This also, I hope you have an understanding of applications here at the bottom, different applications of steel. So effects of, this was a question that the full-time students had written. They had their exam on the 15th. Effects of carbon in the carbon steel. This was one of the questions, and unfortunately it was poorly answered. What are the effects of carbon in carbon steel? It increases hardness, increases strength, while decreasing weldability and decreasing ductility. You know what I said, with increasing content of carbon, what is happening? You are decreasing ductility. So if you're decreasing ductility, meaning you're increasing basically brittleness. And then with increasing carbon, weldability also begins to increase. However, the two pluses that happen with increasing carbon in steel is you're increasing hardness and you're also increasing strength. And then coming to machinability, carbon provides the best. So from about 0.2 to 0.25%, carbon provides the best machinability in this range. That's where the best machinability happens. So increasing carbon content leads to increased hardness and strength. Like I said, it increases brittleness and reduces weldability. That was supposed to be the answer. Maybe I can run you through their paper. Let me share with you the paper that they wrote so that you have a view of what they had. Let me just open the paper for you, share the paper with you. So final exam, you'll be provided with graph paper. Oh yeah, when we meet, we're going to go through the graph paper questions under the mechanical properties of materials. So you'll be provided with graph paper as well as the periodic table. Can you see my new presentation? Can you see the exam
Yes.
paper? Able to see it?
Yes, we can see.
Okay.
It's very visible.
All right. So it's a 3-hour paper with 7 questions, for which you'll be asked to answer, to attempt 5 only. And usually question 1 is compulsory. It will be compulsory in your case also. So this is question 1. This was their question 1. So you just, we're going to plot this together anyway in class. This is very easy. But then time usually is wasted on plotting this. That's why when you come for a residential, make sure you carry enough graph paper, because I want us to practice as much as possible where we can. Plotting of these graphs, because that's where students waste a lot of time on trying to plot this graph before they even come to answering the questions. You find 1 hour, someone is struggling to plot this graph. 1 hour. Giving them with only 2 hours